All right, welcome to the third and final video for today's lecture, where we're going to be introducing the topics of velocity and acceleration. In particular, we are going to be focusing on average velocity and average acceleration. However, as we talk about a little bit later, typically that average value is going to be, or the fact that it's the average is going to be dropped fairly early on, and unless we're talking about another velocity or acceleration, we will have to explicitly discuss it. So let's talk about speed. So speed is how fast an object is going. If you've ever been in a car, they have speedometers. They tell you the speed of your car. And I'm going to assume that all of you are good students at this point. I have no reason to believe otherwise. And you guys go the speed limit. So that could be, in a residential zone, 25 miles per hour. On the freeway, in a non-construction zone, typically it's 65 miles per hour. Some locations it might be 55, and if you're on Highway 5, it's 70. Right? There's a speed, how fast you should be going, at least in California, is limited. In places like the Autobahn and parts of Hawaii, you have a speed minimum instead. However, right, that still you have to be going a certain value for how fast you're going. Now, the interesting thing about speed is that it's a scalar. Right? If you're in your car and you're driving around, you can turn and your speedometer doesn't tell you that you've turned. It tells you you've probably slowed down to make the turn, or you've sped up if you came from a stop. So it'll tell you how fast you're going around the turn, but it doesn't care about any sort of direction. Now the SI unit for speed is going to be meters per second, distance per time. So if this is the SI unit for speed, it makes sense that the equation for speed, and in particular, the average speed, is defined as the distance traveled divided by the time interval traveling, or d divided by t. Now here it's important to note that we are talking about the total distance that you are traveling. Every little part of a meter that you go needs to be included in the total distance that you've traveled. For time, it is every second you are traveling. The second you start moving to the second you stop at your final destination. So if you're stuck in stop and go traffic, you need to make sure you continue counting all of that time. Right? It's the entirety of the time you are traveling and the entirety of the distance you've traveled. Now, again, speed tells us how fast an object is moving, but it doesn't give us a direction. So we want, as physicists or people studying physics, we want more information in a majority of cases. We want to figure out, where are we going? Right? If you're told you need to drive an hour going 65 miles an hour and you'll reach your destination, but you're starting, within 30 miles of the bay, there's a chance if you just drive, are you going the right direction? Right? You can only go so far west before you run into water. So what are you supposed to do? You need a direction associated with it. And so for that, we need the velocity. So the velocity is going to be a vector. You know what else is a vector that we've already discussed this lecture? Displacement. So displacement is a vector that we've defined and says that it tells us the distance and direction an object is moving. Right? It tells us, if we're talking about one-dimensional motion, if we're moving right, left, up, down. And it tells us the value. If we have a coordinate system, it tells us how far to the right, how far down we are moving. And so if we take that displacement and we divide it by the amount of time between those 2 points, we get what is referred to as the average velocity. So this equation here is our equation for average velocity as a vector. Because displacement is a vector, time is a scalar, so it's just telling us how much we need to change, or we're just dividing by a number in this case. Our resulting value is going to be a vector, v standing for velocity. Here, again, we have our displacement, delta vector r, divided by our scalar time gives us the average velocity. Now, moving forward, very often in the textbook, we're not going to be using the average portion when writing out velocity. We're just going to be using v with the vector over it. The reason this is going to be the case is very rarely are we going to be discussing the other type of velocity, which is instantaneous, the velocity at a very specific time. So moving forward in the textbook, typically you will just see v with the vector over it. It stands for average velocity, but because that's typically what we're going to be using. So let's talk about velocity on a motion diagram. So again, we have our equation here for velocity. So we need a direction associated with it. And because of how we're typically going to be setting up time such that our first image is that time is equal to 0, all of our times should be positive. So we're taking our displacement and we're dividing it by a positive number. So that would indicate that the average velocity is pointing in the same direction as our displacement. So here we just have some sort of motion diagram. We don't know what it is, but we know it's moving in the classically negative y direction. And if we look at the points, it is speeding up because they're getting further apart. So let's first draw in our displacement vectors. So we're just going to connect the points with our lines. Right? We have drawn our displacement vector. Now we need to recall one thing about our motion diagram. There was something important said about the points. They aren't an equal distance away, but they're an equal time interval away. So the same amount of time passes between point 0 and 1 as 3 and 4. So because of that, they are going to be essentially the same on a motion diagram because it's the same amount of time passing between each point. So to draw the motion diagram, instead of writing out the displacement, we can instead, I don't want displacement. Instead, I want the velocity. It's telling me the same general thing, but now I can say, it's not my distance between them getting bigger, it's my velocity value getting bigger. Now I can explicitly say I am speeding up, and I'm accurately describing an increase in speed because my velocity vectors are getting longer. And my velocity vector getting longer indicates that my magnitude is increasing. So with a motion diagram, we still connect the dots, but we call it the velocity between our points, not the displacement. Because now it's more correct to talk about how we can speed up or slow down because we're looking at how our velocity value changes. Now you'll notice I'm still using the terms speeding up and slowing down if I'm talking about the velocity. And that is because the magnitude of my velocity is speed. So we don't want to say we're velocitying up or velocitying down, because that just sounds silly. We're speeding up and slowing down. We're changing the magnitude of our velocity. The velocity aspect that's different from speed is the direction. So here we are speeding up in the negative y direction. So the speeding up changes our scalar value, while by saying it's down, that is the velocity component, the direction component being added to our motion diagram. So yeah, the length between our particular points is the average speed between those points. Because again, the average velocity is equal to speed plus, well, I don't know what happened there, direction. Whether we want to just, in this case, because we're focusing on one-dimensional motion, negative x, y, positive x type thing. Now, in this motion diagram, we are speeding up. We are changing our velocity. So we want some sort of way to indicate that we are changing velocity. So in the overall span of velocity, there are two ways we can change our value. One is we can change our magnitude, we can change the speed. So that is our speeding up and slowing down. The other thing we can do is we can change direction. So instead of going just in the x direction, maybe I'm going in the x direction and I start moving in the positive x or the positive y direction as well. Right? I've changed my direction. My angle has changed. Or maybe I'm going in the positive x direction and then I realize, oh, I don't think I locked the door. I turn around and I walk back. Right? I'm now moving in the negative x direction. So I need some sort of way to describe how my velocity can change. And for that, I'm going to be using acceleration. So acceleration is defined as the rate of change of velocity. Acceleration is also going to be a vector, and it has the SI unit of meters per second squared. So m per s squared. And the way that we know that it is this, so we have meters per second. This simplifies down to meters per second squared. So we are looking at the rate of change of our velocity, where velocity was the rate of change of displacement. I know some of you are currently in Calculus 1, so you've probably seen this rate of change thing popping up quite a bit already in your class, where you're talking about how does something change. So we need to figure out an equation that tells us. So right now we are sticking with algebraic relationships between displacement, velocity, and acceleration. As we move forward a little bit in the class, we're going to get into a calculus relationship between displacement, velocity, and acceleration. And so right now we're not using calculus, but the same thing we're discussing now can be used with calculus, and we'll be doing that in a little bit. So let's look at the algebraic equation for linear acceleration. So here we have our average acceleration. So our variable for acceleration is a, and it's the change in displacement divided by the change in time. Again, this delta symbol is final minus initial, or final minus starting, whichever term you'd like to use. This delta symbol always represents the same thing. So if we were to have a final value for our velocity and some initial value for our velocity, we could, in a time it takes to make that change, we can have an acceleration. Now, in things like car commercials, they never tell you about the acceleration, but they always talk about the change in speed. How long does it take to go from 0 to 60? That tends to be the common thing that talks in car commercials, like 2.3 seconds to go from 0 to 60 miles per hour. We could go through a bunch of unit conversions and get the acceleration of that car in meters per second square if we wanted to. It's possible, but it's a fancy way of talking about how fast can this car accelerate. When they're talking about braking, it's talking about acceleration still, but now there's a directional component of acceleration that we are considering. And we'll talk about the difference of speeding up and slowing down relating to acceleration and terminology in the next lecture. So right now, we just want to focus that acceleration is the change in velocity over a change in time. So naturally, we want to include this on our motion diagram. So the average acceleration vector is going to point in the same direction as the change in velocity vector. Because again, in this equation, we're assuming that our change in time is positive because we started at time is equal to 0 and we've gone to, let's say, time is equal to 10 seconds. Final, 10, minus initial, 0, is a positive number. That's going to result in acceleration pointing in the same direction as our change in velocity. So this here is referred to as a tactics box. So these are scattered throughout the chapter. Typically, they tend to occur once or twice, depending on the particular chapter. This is 1.3, so there have been 3 of them at this point. We've skipped the other 2 because it's graphical addition. This one is still graphical addition, but it's a lot easier to digest. But so it tells you, I know the student workbook isn't required, but if you, for some reason, purchased it, it has some explicit exercises you can connect to. It's usually at the end of a section, so you can read the tactics box, and if you have questions about it, it's in the section that it is contained in. And they usually just kind of help you go through and solve something. So this one is finding the acceleration vector, in particular using a graphical method. So here we have some initial vector, some initial velocity and a final velocity. And basically the way that you go through and do this, again, I'm not going to be requiring you to go through and graphically do this, is the difference in their size and the direction is how you draw the acceleration vector. So here, our velocity vector is pointing in the same direction. However, our final velocity is bigger. So as long as you drew the acceleration vector in the direction that, it's speeding up, so the velocity needs to point in the same direction as acceleration points in the same direction as the change in velocity, that's fine with me. So you don't have to go through all of these steps. I think in the next slide I actually have an example. So let's look at that instead. All right, so this one, I'm not going to have you pause it. I'm just going to go through it to kind of talk about motion diagrams and what I'm expecting originally. There is another example after this that I will expect you to pause and go through. So we have a goose. It is flying towards a pond. It's going to land on the water and slide for some distance before it comes to a stop. We're drawing the motion diagram of the goose starting shortly before it hits the water and assuming the motion is entirely horizontal. So reading this question, there's a couple of key things that I need to be aware of. So the first thing is my motion is going to be entirely horizontal. So I'm going to have all of my motion explicitly in my x direction. So I'm going to be using the standard coordinate system. It tells me it lands in the water and slides for some distance before it comes to a stop. And I'm being asked to draw the motion diagram of the goose starting shortly before it hits the water. So what I'm going to do is to help me personally draw my motion diagram, I'm going to give myself some water. So when I draw my motion diagram, I'm going to have my goose coming in. Now, I'm not going to actually draw a goose. I'm going to draw a point. So I have some goose coming in. And it's coming in at a constant speed. I don't know that, but it says to draw before it hits the water. And I just think geese are aggressive and they're just going to come at the water at a very given speed. They know what's going to work and what's not going to work. So they're coming in. Let me give myself a little bit more space between my points. So I have my goose and it's coming in. At this third point, we are now going to be hitting the water. I'm going to draw my points above the water for now, and then I'm going to erase my water, and then I'll put it, or I'm not going to erase my water, I'm going to leave my water here, but I just know that these points are in the water. Because what I'm doing, actually I should line it up with my point, is now I know that my goose is going to slide for some distance before coming to a stop. So because it's sliding some distance before stopping, I need to slow down. So that means that my next point should be a little bit closer. And then my point after that should be closer still. And my points should get closer and closer to each other until my goose stops. So it can look something roughly like this. Now there's not enough information in this question for me to tell you the goose takes longer to stop. It's some distance. It wasn't an instantaneous stop, and my goose has slowed down. So I now have my points. I need to now go in and draw my velocity vectors. So I'm going to have, that's about the same color. Let's do this in green. So I have my velocity vectors. In theory, the two of these are the same. So I'm just gonna write myself a note and say these are the same size. So if you are worried about drawing a motion diagram and you're worried it's not going to look good, it's okay to leave me notes. I'll read them. I had a student draw a motion diagram and they didn't give themselves enough space, and so they moved it to the back of the page and they wrote like, hey, I ran out of space, see back. It's fine. If you want to indicate, hey, these are the same size and you didn't use a ruler like I have it here, and they happen to be a little different, that's fine. It's okay to leave me notes because I'm not expecting perfection, like I said. but if you're worried about it, a note is always okay. So I now have hit the water, and my velocity vectors start getting smaller. In this last one, it's really hard to draw between it, so I basically have a little line. This is not a complete motion diagram. I need to include the acceleration as well. So I'm just going to write myself a note over here that this green color is my velocity. And now I need to have my acceleration. I'm going to do that in orange. So I need to think about what's happening. So because my pre-water, I'm saying that my goose isn't slowing down, my change in velocity is 0. So therefore, I have 0 acceleration vector before my goose enters the water. It's once my goose hits the water that I start to slow down. So that means that if I was to do my equation for acceleration, right, I have my final velocity minus my initial velocity divided by my change in time. My initial value is larger than my final value. So I'm going to have a negative value for my acceleration. Because of this, my acceleration needs to point in the opposite direction as my velocity. So my acceleration vector needs to point to the left. The same thing is true with every single one of my points. It should point to the left because that is how my acceleration is changing. Now, traditionally, for our motion diagrams, the acceleration is drawn above the point, because that way we don't have a bunch of lines in the same place. Now, my acceleration value here isn't constant. That's just because I've drawn points really poorly. The textbook is going to draw it in such a way that the points are constantly spaced. So let's go ahead and let's look at an example for a complete motion diagram drawn to scale and all of that. So here we have a motion diagram. It is a two-dimensional one. So we have our velocities given, and then we have the accelerations as well. So in this question, you're being asked to write a 1 or 2 sentence story about a real object that has this particular motion diagram, and you should be explicit. So go ahead, pause the video, and solve or write out your story. Okay, so there's no one correct answer for this motion diagram. There's a lot of different things that undergo this particular behavior. I'm going to have some snowboarder. My personal favorite snowboarder, I guess, is my brother, because I know him. So I'm just going to, say Doug snowboards down a hill. He's picking up speed, right? The acceleration and the fact that my velocity values are getting larger indicates that he's speeding up. So he snowboards down a hill, speeding up. He's then getting to this flat part. So I'm going to say at the bottom of the hill. And now if I look at my velocity vectors, they start to get smaller. I'm slowing down. In this particular image, as it's drawn, he doesn't stop. So I'm going to say at the bottom of the hill, he begins to slow down. This is 2 sentences that explains the motion of this particular motion diagram. Now, did you have to use Doug's snowboarding? No. You could have done anything that speeds up as it goes down and to the right and slows down once it's only moving in the right direction. So as long as you have that description, that is fine. And again, I just want to point out that this image here is a complete motion diagram. We have our points, so our positions, we have our velocity vectors, and we have our accelerations. So this is going to wrap it up for today's lecture. Please make sure to take the lecture quiz if you haven't already. And if you have any questions, please let me know.